I've been to India? No, but I did give a talk in India last week, virtually. So would love to visit someday. Now, I think it's about time we get started. So we're thrilled to roll out the latest episode of the Quantum Seminar series dedicated to the research and academic communities. The seminar takes place every Friday at noon Eastern Time and will be hosted on the Qiskit YouTube channel. And so I'm delighted to see so many of you already tuned in to this channel. I'm your host, Zlatko Minev from IBM Quantum Research. And it is my pleasure to introduce Antonio Mezzacapo from IBM Quantum Research today. Hello, Antonio.
Hi, Zlatko. How are you doing? Thanks for the introduction.
Yes. Where are you tuning in from today, Antonio?
I'm actually in Italy, so it is a beautiful sunny day. I was enjoying the sunshine before my Qiskit talk, and your nice introduction. So
yeah. Well, I hope we can make this also as enjoyable as the sunny day in Italy. Although that will be a tough one to get to today.
let's aim for that.
Let's aim for that. I hope the audience can help us with their good questions. Antonio will present some very nice results that came out recently on machine learning at the Quantum Classical Computational Frontier. Antonio is a technical lead at IBM Quantum. He studied in Naples, and did his Ph.D. at Basque Country. He was a postdoc at IBM, then a research staff member, and then a technical lead in a very quick period of time. And I also have the pleasure in 2 weeks, I think, to lecture side by side with Antonio in the Qiskit Global Summer School. I am pleasantly shocked by the 5,000 people who've already signed up for that. So the lectures will be posted online. I know we might have closed the sign up at this point, but I think those lectures will be public. So you can see Antonio and myself again in a few weeks. Maybe Antonio, you can begin to pull up your slides as I give a little bit of the format and some of the takeaways.
Yes.
This talk is aimed at studying the advantages that come at the interface of quantum and classical computing. How can we generate advantage in handling classical to quantum? Or as Antonio will introduce in a few slides, what can classical machine learning do for quantum? Somewhat the flip question of the one I think we talked about in the last seminar. And it will cover 3 papers. So the question and answers are interactive during the talk. You can ask them in the comment sidebar. And I think with that, it is my pleasure to hand it over to Antonio.
Okay, thanks again, Zlatko. And I guess you can see the slides right on the screen. So as Zlatko was saying, so this talk is about machine learning at the quantum classical computational frontier. We will see what I mean by that in a few slides. Well, let's begin with this overview. So there is currently a lot of ideas around on what quantum computing can do for machine learning. So when we speak about this, it's what usually people call quantum machine learning. Okay, and this is an IBM perspective on that. So last year we have shown that a binary classifier augmented with quantum kernels can make use of a feature space which is embedded in a Hilbert space, and hopefully this embedding in this Hilbert space used as a feature space could provide some kind of quantum enhanced classification for classical problems. So this is what this goes into the direction of what quantum can do for machine learning, but this talk, it's not really about that. Okay, so this talk is about this question, can machine learning help enhancing quantum computing algorithms? Okay, so I want to use classical machine learning tool to have my quantum algorithms run better or enhance their performance. And to do that, I'm really gonna take the computational chemistry route. So I'm going to show that indeed, yes, machine learning can help quantum computing, and especially in the space of quantum chemistry applications. Okay, so it's really these three nice. This talk really lives at the intersection of these 3 interesting areas. Yeah, but before turning on to the machine learning, I'd like to give a bit of a background on what we have been doing about quantum chemistry using quantum computers at IBM. So let's start with this work that we did 3 years ago. It got published in Nature. So what we studied here, we studied the performance of a variational quantum eigensolver used to tackle molecular problems up to beryllium hydride in size. We used the hardware fission ansatz, and the results were pretty good. But really, the question that we keep asking ourselves is how we can get better and better. So how can we devise better algorithms to tackle quantum chemistry problems or your favorite many-body interacting many-body problems, right? And this kind of question brings us to this slide. And these slides, there are what I think are the current challenges for using quantum computer to target quantum chemistry applications. You see on the left side of the screen, there are what I think the main quantum algorithms that we can use to target quantum chemistry problems. So you have the phase estimation, of course, quantum dynamics. I want to simulate my chemical systems when it's not in an eigenstate. Of course, variational quantum algorithms that allow us to target ground state properties of chemical systems, and subspace methods to get excited state properties. But when you look at all these available algorithms, you quickly realize that they really boil down to a couple of subroutines, which are Hamiltonian simulation and Hamiltonian averaging. And so if we want to improve on these two subroutines, well, we can split them into a bunch of challenges, which I colored in blue and yellow to mark them as hardware or experimental or software or theoretical challenges. So of course, the hardware challenges are reducing readout measurement errors. I want to have better control of my gates, sampling speed. Of course, we want better coherence of our qubits. And on the theory side, what we want to do is optimize gate sequence. So if you think about Hamiltonian simulation, I want to do that using less and less gates. I want to use better bases to describe the same problem. A better basis will allow me to simulate that problem more efficiently, and so on. Better qubit encodings, error mitigation schemes to deal with finite error rates that we have on our devices, and measurement precision, which is going to be the focus of this talk. Now, I like to say, so even if all these challenges here help in our NISQ era, so the current era we live in which we have only access to quantum computer which are not fault tolerant, so in which the decoherence is still on, playing a role in the outcomes on our simulation, I think making progress in each one of these areas will also have an impact when we're going to have fault tolerant quantum computers, right? And then, okay, so this talk is really going to be about measurement precision, which really plays a big role in running variational quantum algorithms. And the reason for that is, so think about what we do when we try to optimize a given cost function to, for example, get to the ground state of some molecular problem, but also some classical cost function, right? So what we do is typically we use some gradient descent method or some optimization method, and if the function that you're trying to optimize, so the molecular energy in this case, has some stochastic noise on top of it, that will make the optimization much harder, right? So it's really hard to optimize something which has noise on top of it. The gradients that you're going to build, they're going to have noise. Whatever technique optimizer that you can use is going to be impact because of that. Okay, so there are also some very good stochastic optimizers, but really what we want to have is a cost function which has less noise. And also, error mitigation techniques like zero noise extrapolation are also tied to the precision in the energy estimation, right? So think about zero noise extrapolation, which is what this plot is showing from our results last year. So what you see here, it's the calculated energies, so calculated dissociation profile for the hydrogen molecule and lithium hydride at different distances. I think you should be able to see my laser pointer. Yes. Okay.
Yeah,
so
yeah, we can see it.
Yes. So these colored dots here, they are estimation of molecular energies at the final point of a variational eigensolver obtained for a different effective level of noise. Okay. And then, so what we do with the zero noise extrapolation is we observe the behavior of the the measured energy as a function of the noise, effective noise that it's acting on the system, and then we linearly extrapolate to get to these blue dots here that you see. They pretty much fairly well capture the full CI energies for this molecule, right? But that, now think that each one of these dots, these colored dots here, has some fluctuations on top of that. So if you try to do a linear extrapolation with noisy points, of course the extrapolated point is gonna, it's gonna feel the error due by the stochastic fluctuations that you had on this. These points here. So I guess that the message here, what I'm trying to communicate, is that precision in the energy estimation, so the precision with which we can measure things on quantum computer matters. It matters for a lot for variational algorithms, but it also matters for ideas such as error mitigation via zero noise extrapolation. So, okay, we have this problem. We want to get precise measurements. So let's see where does this problem really come from. So let's start from a trivial case. Okay, there's nothing more trivial than 1 qubit for quantum computing. So let's start with 1 qubit. So I have my 1 qubit prepared here in the, if you want, the Hadamard state. So it's an equal weighted superposition of up and down 0, 1. And then I take the state and I try to estimate the mean value of x or the mean value of z. So I measure in these bases, and of course if I measure in a basis of eigenstates of x, what I'm going to get, it's always the same answer, because the state is prepared in an eigenstate of x. And then if I try to measure z instead, in this basis, this is not an eigenstate, so I'm going to have fluctuations in my measurement outcomes. Sometimes I get 1, sometimes I get -1. And this is what I mean by quantum noise in these slides. Okay, there's other people that use the word quantum noise in different contexts, but this is what I mean here. And this is really the noise. We will see that this is really the noise at the end that we feel when we try to measure, when we try to estimate molecular energies. But so, okay, so now I got my measurement outcomes for the z and x basis. Okay, now I want to estimate the mean value of x and z. So what I do is I take the measurement outcomes and I just just average them. Okay, so I take the mean of these measurements, and of course the error for that for x is going to be 0. Because I had access to a measurement basis of eigenstates for this operator, right? And the mean value of z instead, it's gonna have an error which is gonna go down to 0 as the inverse of the square root of the number of measurements that I'm making here. Okay, this is just the central limit theorem, and in general for a generic observable, this is how the error is going to scale. Okay, so it's going to be at the numerator characterized by the variance of that observable, and denominator it's going to have the square root of the number of shots. Okay, so then this feature, this description for 1 qubit, it can be ported to the case in when we try to estimate these complex chemistry Hamiltonians. So what they are really, they are linear combination of Pauli operators, which acts on n qubits, weighted by some real coefficients alpha I. And then, just as in the case of the X operator before, we really would like to measure this operator in its eigenstate basis. But of course, this is not possible on the current devices that we have. What we really have is just single qubit projective measurements. Okay, so armed only with this single qubit projective measurements, we want to estimate an object which has this complexity here. And this is a problem because even if we prepare the perfect ground state for this object, so estimating the mean value of H only armed with single qubit projective measurements will have an error which it's going to be the error it's going to be bounded by this formula here. And think of this dependence here on the low right part of the slide here. So the number of measurements that we have to take to estimate H at fixed precision when our molecular or fermionic problems go up in size goes roughly with the eighth power of the number of fermionic modes, which are little n here. So it's really a lot of measurements, and this sometime, well, I would say this actually is one of the main bottlenecks of variational algorithms. Okay, so not only decoherence, but also measurement precision plays a role.
And so, Antonio, this is a really kind of key formula. Maybe we can deconstruct a little bit. So I guess m, the value m here is 4 to the n, because you have 4 Pauli operators per qubit, and
in general, in general, it's gonna be 4 to the n. But of course, like realistic system, maybe, you know, they have like little slower dependence, maybe n to the 3, but yes, worst case is n to the 4, yes. So that's where you get this n to the 8 here.
Right, and I guess unless you use symmetries and so forth, you don't know what the support is within that 4 to the n. But where does the n to the 8th come from that? Or I guess that's a separate maybe.
Oh, it's the product of S by M. So M is the number of Paulis here of your Hamiltonian, and S is the number of shots per Pauli term that we have to take to get this error.
I see. Thanks.
Okay, so it's a product of 2 n to the 4, right? So the number of shots has to go as n to the 4. The number of shots per Pauli term has to go as n to the 4 to keep this error the same, right? And then you're going to have an n to the 4 coming from number of Pauli terms that you have in your problem.
Yeah, so the condition here is keeping for a fixed error. Yeah, you want to scale s as n to the 4th, and because you also have the sum in the top, then you end up with another n to the 4th.
Oh, yes. So there is the sum in here, but this s here, remember, it's the number of shots per Pauli terms. So then we have m Pauli terms, so you have to multiply that. Okay.
Good. Thanks.
So okay, so it's a lot of measurements, and then if you want to do this the trivial way, the naive way, what you will do is run this circuit. So first we prepare the state we want to make our measurement on. So this green area here could be the circuit that prepares the quantum state at the end of a VQE. Then once our state is prepared, we want to estimate separately each one of these Pauli operators Pi. And so what we do is we put ourselves in a basis in which this Pauli operator is diagonal just by running some single qubit rotation, right? And then doing this for every Pauli produces a data set of Pauli measurements. And the easiest way to get an Hamiltonian estimation with this data set is just by averaging mean values for each one of these Pauli operators separately. Okay, then, so here you can see that the title of the talk start to make some sense, right? Because what we have here really is some quantum processing on the left side of the screen, in which a quantum computer prepares a state we want to do our measurement on. And then what I mean by quantum classical frontier is the act of taking these measurements, really. Okay, so how do we take this measurement? What's the best way of getting these measurements? And then there's going to be a step of classical processing, which in this most trivial case, it's just averaging the measurement outcomes that I've taken in this yellow part. Okay, but this is the most like the naive way of doing this, and we're gonna see in the following slides, in the rest of this talk, how we can complicate the scheme to get better measurement estimates, right? More precise measurement estimates. All right, so we already realized 3 years ago that going through each Pauli is not the optimal thing to do. So indeed, several Paulis can be estimated by using the same measurements. And the way of doing that is group Pauli operators in these sets. So here in this box, I think you see in this table, you see the lithium hydride Hamiltonian. And in each box of this table, you see Pauli operators that can be measured together in that can be estimated with the same measurement outcomes. Okay, so this is better
you mean,
than
for
just,
example, such as measuring Zi and Iz can give you Zz?
Yes, and so the condition is that on each qubit, you either have a certain Pauli operator or you have the identity. You cannot have two different Pauli operator, non-identity Pauli operator for Paulis that belongs to the same box. Okay. Now, of course, there's a lot of questions here. Of course, one question is what is the optimal way of doing that? Actually, it's very hard.
Right, is that the same as saying that if you take two operators that commute, then you can also find the product of, or no?
No, this is more than commuting. This is actually qubit-wise commuting. Okay.
Oh, qubit.
So if two, yes, so they have to commute qubit by qubit. So if two operators commute, then in general you can measure them together, but you have to find the unitary transformation that allows you to measure them together, and this can be sometimes not an easy task. If they qubit-wise commute, that operation, that unitary that allows you to measure them together, it's just a single qubit rotation. So we really want this. Actually, this is a perfect introduction for this next slide. Thanks for the question. So since we started grouping operator in this way, then there has been a lot of research on this kind of topics. And so a lot of people have come up with techniques that reduce the number of measurements to get precise estimations of complex operators like the molecular energies. But some of these techniques actually they add to the depth for the state preparation. Okay. So you get a reduction in the number of measurements, but you also have to run circuits which have higher depth. So given the fact that we don't really have fault-tolerant quantum computers, our quantum computers are noisy, we want to do the least amount of gates as possible, what we would like to use is something that do not increase the circuit depth for this task. And indeed, there are some work which have been considering how to improve this measurement precision without increasing the depth. For example, this work here. And typically, the research along this direction it's based on better heuristics to group these Pauli operators into qubit-wise commuting sets. Remember, that's an NPR problem. So if you come up with a better heuristics for that, it's going to be better. And then lately, there has been also some research aimed at retrieving generic properties out of quantum states. So here the question is not really, I have a very complex Hamiltonian operator that I want to estimate, or I have a complex observable that I want to estimate, but really I want generic properties of reduced density matrices or k-qubit reduced subsystems. And so the last work, actually, which has the optimal scaling for this kind of task, is this work by Huang, Kuang, and Preskill, which uses the idea of classical shadows. Now we have picked on this idea, and we have tried to build an estimator, not for generic prop. Yes, question.
Sorry, not to interrupt you moving into the next slide too quickly, but curious. So this obviously has a lot of relationship to things such as quantum process tomography, quantum state estimation, and so on. Is there much more to say here about how, in the quantum, say, process tomography, maybe you need to prepare all the initial different, states you might need to run through your algorithm. Here, you only need to measure all the polys coming out at the end. But how much of a relationship would there be, or is there, between the two communities?
So yes, the question here, it's much weaker than the tomography question, right? Because so here we're only interested in local observables. So we're not interested in characterizing the full state with its full-fledged exponential number of features, but we only want to, for example, estimate all the k-qubit correlation functions, right? On all possible combination subsets of k-qubits in your system. Okay, so
you mean like sparse in some way, like sparse tomography, in a way, or?
Yes, I mean the goal is different. So we want really characterize subsystems, really. Okay. Mm-hmm. Because at the end, physics is local, right? So any physical property that you try to estimate, it's typically a linear combination of local observable, right? So if you want in electronic structure problem, the Coulomb interaction, they decay, right? So they decay with the distance. So you're never going to have, you're always going to have local operators. And also interaction higher than two-body are negligible and so on.
Yeah, except maybe for special phenomena like superconductivity or things like that, where you can get more non-local, like beyond Hartree-Fock things.
Yes, but I think, okay, now we're steering.
Sorry.
No, I think, the BCS Hamiltonian still, you can write it as as a linear combination of local. When I say local, it may be local in a certain basis. That doesn't have to be spatial. Yeah. Right. Doesn't have to be spatially local. It can be, for example, local in the momentum, right? That's what the BCS Hamiltonian is, right? So exactly. Okay. So all right, but really the focus of this talk, what we want to tackle here, is we want, as I say, I want to measure observables which are complex and are linear combination of Pauli operators, but we're going to see that we're going to use some idea from general k-qubit partial tomography. Okay, so the idea, so the idea of this slide, this is a one-slide summary of the result by Huang and co-workers. So what they do in this classical shadow paper is that they prepare a quantum state as usual. Then, since they're not concerned in retrieving a particular observable, what they do is just they start measuring that state on random basis. Okay, so they draw a basis at random, x, y, z basis for each qubit, and then they gather together all the outcomes of these measurements in a data set, and they call this data set a classical shadow. And then at the later stage, they can query this data set. They can take measurement from this data set to estimate observables that somebody at a later stage is interested in retrieving. So again, we have that you see the structure here, which is similar to the naive way of measuring Hamiltonian, the previous stage that I showed you. So we have a quantum processing section of the algorithm. We have a quantum classical frontier in which we make measurements, which are optimized for the tasks that we want to achieve. So in this case, it's going to be random measurements because we are interested in retrieving a collection of generic observables. And then at the end, there's the classical processing stage, which in this case comes later, right? So it comes with no knowledge of the of one particular observables that we wanted to estimate. But again, so what we want to do is take that idea and use it for somehow tweaking it, modifying it for retrieving just one observable. So we take this classical shadow idea and let's write it down how it would look like if we only were interested in retrieving one observable. Okay, for example, the complex molecular energy, a complex Hamiltonian made up of a linear combination of many Pauli operators. So what we will do is we would embed this measurement scheme with the classical processing scheme, right? So what it would look like is this. So for a bunch of shots, for a bunch of measurements up to big S, we prepare our state and we uniformly pick at random a certain basis. Pick the random on X, Y, Z direction for each qubit, and then for each qubit we will measure these qubits in the basis dictated by a PI, and which is the ith qubit component of P, and then provide a measurement outcomes, which is mu PI, and then we would start building up our building up an expectation of our observable, which will look something like this. So it will be a weighted sum of these measurement outcomes weighted by this function f, which actually weights, you see the definition here. So it weights basically the chances that by drawing a Pauli at random, we end up with a Pauli which was present in the original Hamiltonian. Okay, so this is the definition right here. And then, so this will be our one-shot estimator for H. Then we would average this over many shots to get the estimation of this operator H with classical shadows. Yeah, but we thought, okay, this is not really the optimal way of doing that if we are only interested in retrieving one observable. What one could do is, instead of randomly pick the measurement basis in each direction for each qubit, now we could start off biasing the choice of this measurement basis with distributions beta. So you can think of beta i's as a distribution defined along the XYZ direction for each qubit. Okay, so it's a distribution where we sample from to determine the measurement basis for our n qubits, and then we would just we would go along and do the same stuff that we did in the previous slide with a difference. Because the difference is now that this function f with which we weight the measurement outcome, it's now has this beta factor in. Okay, so it takes into account the fact that we are not sampling at random in the XYZ basis, but we have introduced this bias. Okay.
So this is really cool.
Yeah.
Oh, sorry. Wait,
please.
I might be jumping the gun here, but I'm curious. So the initial one is supposed to be, in some sense, like an unbiased estimator for a finite number of samples. And then here, when you introduce this bias in the sampling, does that also potentially make you biased for each? Do you know what I mean?
Yeah, no, maybe there's a bit of confusion. So the estimator that we get here, it's still an unbiased estimator for the thing that we want to estimate. Okay, So what is biased here? It's the
distribution.
the distributions from which we are sampling from to get a measurement basis for a given shot. Okay, but the final estimator is still unbiased. So it's this f function, if you want, corrects for this bias of picking non-uniformly picking every qubit in the XYZ basis. Okay, so at the end of the day, this is an unbiased estimator.
Yeah. Okay.
Mm-hmm.
Yeah, I was just concerned in the limit of finite samples if you run away from that, but I think I'm good.
Yeah. Okay. Okay. So why we're doing this? Now we have introduced this degree of freedom, right? So we have introduced these betas distribution, which we can change for each qubit. And let's use to our advantage the degree of freedom beta, right? So how do we use it to our advantage? So suppose that the state we're sampling from, it's not very far from a reference state. This is actually a very fair thing to assume for quantum algorithms that tackle ground state problems, because every quantum algorithm that tackle the ground state problem has to start from some kind of reference state. So VQE has to do that, but also phase estimation, right? So also phase estimate, the starting state of phase estimation has to have a non-vanishing overlap with the ground state you want to get the properties from. So this is a fair assumption. Okay, so we are targeting quantum chemistry applications. So what is a good reference state for quantum chemistry? The Hartree-Fock state. But in general, of course, all that I say here, it's based on quantum chemistry, but you can think of porting this procedure to your favorite condensed matter or many-body system problem. Just all you need is a reference state and a Hamiltonian. Okay, so reference state. With the promise of this reference state, now we can actually write down analytically the variance of the estimator that we have defined in the previous slide on this reference state. This is the expression. And now you see that this expression contains the distributions beta. And since it contains the distribution beta, now we can choose the beta to minimize this variance. And if you do some algebra, some calculation, it gets down to optimizing this cost function here. So minimizing this cost function, which is now a function of your original problem, the Hamiltonian. You see the alpha is from your Hamiltonian, the distribution beta, and the MI, which are the the occupational number that characterize your reference state. And then that's what we do. We optimize this cost function. We pick, which is an efficient procedure. We pick the optimal beta. We put it back to the estimator, and we've run. We can now use our optimized estimator. Also, let me tell you that actually with a bit of a tweak, so just reducing this cost function for just diagonal terms, so neglecting, terms here in which Qi is different from Ri, we get what we call a diagonal cost function, which is actually a convex. So it's really efficient to optimize. Okay, so this is the results that we get. So we have studied the performance of our locally biased classical shadow estimator. I didn't tell you, so we call this procedure of biasing measurement basis for each qubit locally biased classical shadow. Okay, so we benchmark the locally biased classical shadow estimator against other estimators which do not increase circuit depth. Okay, so we want to fix this parameter. And we have benchmarked it against L1 sampling, which is just estimating Pauli operators in your Hamiltonian, but this time sampled by according to the L1 norm or their coefficient. With benchmark against grouping Pauli operators using a large degree first heuristics and the original classical shadow idea of Wang and co-workers. And we see that fairly every time our locally biased classical shadow estimator actually improves in variance on the other algorithms, on the other estimators. And so this is very good for chemistry, it's very efficient, and also as a good thing about this estimator is that we don't need to address NP-hard grouping problem that arises when we try to group Pauli operators that come from complicated Hamiltonians. Okay, so this is the paper on arXiv on this idea. Now I would like to move on. So I promised you that I was going to talk about machine learning. So let me add back the machine learning circle to my Venn diagram here and keep continuing. Okay, so again, let's start from that 1-qubit trivial case that I showed you some slides ago. I initialize, let's recap, I initialize my qubit in this Hadamard state, and then I try to estimate mean value of the Z operator, and the error that I get goes as 1 over square root of S. This is the formula for a genetic observable. And then I ask myself the question, is this the only way I can get an estimation of the mean value of Z? So is averaging the only way? Well, actually it is not, okay? What we could do is make a guess. In this case, we can make a guess for a distribution that models our measurement outcomes. So since we are only concerned with 1 qubit and observable defined on 1 qubit, which is the Z operator in this case, the outcomes that we get are really binary outcomes, right? 1 or minus 1. So this distribution here can be easily represented by, if you want, a bias coin flip, right? Or technically a Bernoulli distribution. So another way of getting the mean value of Z is compute the maximum likelihood of a Bernoulli distribution with bias P computed on the measurement outcomes that I already got from the quantum computer in this case. So what we do, we maximize this function, we get the best value for P, and then once we have the behavior of this function, then computing the average mean value of Z just turns out to apply this formula here. Okay, so this is another way of getting averages. This could give you an advantage in computing, in computing like more precise those mean values. It could give you like a bias estimator, so that there's trade-off here. But the point of this talk is we could simulate our measurements of 1 qubit and Z operator with a Bernoulli distribution. But when we're dealing with quantum chemistry, we don't have a coin flip, right? So what we have is a number of Pauli operators, which scales as the fourth power of fermionic modes in your system, if you want. So it's a lot of coin flips, right? And not only that, these are correlated quantum coin flips. So having a joint probability distribution that simulates at the same time all these measurement outcomes from these Pauli operator, it's a hard task. So the idea that we had is to use a neural network quantum state, to give the neural network quantum state this task of predicting all these quantum joint distribution. Okay, so what's the idea here? Well, the idea is that let's start from a parameterized quantum state. This is a parameterization of quantum state, so it's the amplitude. It's a wave function. This describes the amplitude of getting your qubit or spin configuration in the configuration sigma, described in terms of weights and parameters of a neural network. Okay, so we have a neural network, in this case a restricted Boltzmann machine. So it's a neural network with just one visible layer of variables and one hidden layer of variables, and there is no connection between same layers. And the this Boltzmann machine here, it's described by this partition function here, And then what we do, of course, like this visible layer of variables now encodes our qubits. So you can think of the state of our qubits as the state of the visible layer of the variables of this Boltzmann machine. Again, so to get the state, the amplitude of quantum state over a certain configuration for this visible layer, what we do is we trace out the hidden layer. Yeah, so this sum here, and then this formula gives us the amplitude for certain configuration of the visible layer. In other words, the amplitude of our quantum wave function. Of course, this is not a normal restricted Boltzmann machine. This is a Boltzmann machine with complex weights. If we don't have complex weight, these amplitudes cannot be negative or complex, if you want. And of course, this idea was introduced by Kaleyo and Troyer, 2017. But the idea here is that we will make use of that ansatz to improve our measurement precision. And the way we do that is, as usual, we prepare a quantum state on a quantum computer, the gray part here, for example, final stages of VQE. We have prepared a quantum state. Now we produce a data set, just as we wanted to get the mean value of Hamiltonian by averaging, just the same data set. But the new thing now, and this is where the last stage of that classical processing unit I was telling you before really gets complicated and interesting. So the new thing now is we train a neural network model, which is that RBM parameterized state that I showed you in the previous slide, with the data set made up of measurements from a quantum computer. So we minimize the statistical divergence from probability distribution obtained with our wave function ansatz and what we actually observe on the quantum device. Once this statistical divergence is minimized, now we have a classical object, which is a neural network, and we can query this classical object with whatever question we have. So in this case, we want to retrieve the mean value of complex observables like molecular energies. Okay, so what are the results of this scheme? Well, they're actually really good. Okay, so in these panels here, you can see a comparison between a distribution of energy outcomes obtained with standard quantum computing estimators. So by just averaging the measurement outcomes from each Pauli operator. So you see that, of course, we are sampling from the exact ground state here. So we prepare the exact ground state, and we sample on that ground state all the Pauli operators that compose our Hamiltonian, and then we average them. And we see that, you see how this distribution that we get for a certain number of samples goes like well beyond these red bars here, which I think are set at 1 millihartree or something like that, of the exact ground state energy, which is this black bar here. And you see on the right, you compare an estimation obtained with the same data set. So this left and right panel are obtained with the same data set. But this time here, we have trained our neural network, and after we have estimated the complex Hamiltonian of that neural network. And you see that how much precise are these estimations now. So all our energy estimations fall within this this red error bars, right, vertical error bars. And so what we show in this paper here, published in Physical Review of Research, is that we get 5-6 orders of magnitude improvement in the precision with respect to like simple bounds, and 3 orders of magnitude with respect to standard averaging quantum computing estimation. Okay, so note that this may come at a price. The price is that these estimations that we get now, they're not unbiased. Okay, so they have like note that this all these distribution here are a little biased to the right, and this is due to the fact that we may introduce this bias in the training process. but still, the performance is still much better than just averaging. Okay, so the composition of this bias with the drastical improvement in measurement precision that we get here still allows us to do much better energy estimations. Not only that, but a great thing about this bias is that it is always positive. It is always positive because of the variational principle. So here we are drawing sample from the ground state, right? But if we somehow miss slightly the training of the exact ground state, what we will get is always an energy estimation which is greater than the actual ground state energy. So the fact that this bias is always positive is actually great for variational algorithms, right? It always gives us a lower bound on the energy, which is what many variational algorithms do. Okay, and this is another slide which basically make the point. So the number of measurements needed to get to an accuracy of 1 millihartz, it's much lower for a QC plus NN method, which is quantum computer plus neural network method. So you see for the same amount of measurements, M, which is the size of our data set, the chances, this is a probability on the y-axis, so the chances of getting an energy estimate within epsilon from the real ground state it's much higher for in the QC plus NN case than just in the trivial QC case alone, with the usual estimate by averaging. Okay, but now, yes.
Maybe quick question, just so I understand exactly here the trade-offs. With the neural network, basically you have a much smaller variance or higher precision, but you maybe trade off some accuracy because of the bias, right? And
yes,
in terms of the bias.
So if you define accuracy in terms of the exact ground state energy, the accuracy is actually greater for a given size of the data set. What we are trading off is a possible bias in the energy estimate for that precision, but of course, like that bias depends on a lot of things that can be analyzed and improved, such as like use different neural networks or different techniques from the training and so on. So I wouldn't say that we're trading precision for accuracy, because actually we're getting better accuracies for same size data set.
Yeah, and I guess by accuracy here you mean that if for a fixed, for the same data set, basically I would have a huge variance in the naive way, and then a much tighter variance that maybe isn't centered on the right thing, but it's sort of much closer on average type.
Yeah,
right.
Accuracy,
and then if
and
if I increase my number of, if I increase my samples or whatever, then as the variance shrinks on both of them, then you have some sort of belief that the bias also gets smaller?
Yes, no, the bias does get smaller as you increase. Of course, the bias can only get smaller if you improve your training, which means the one way of improving the training is actually sampling from a larger data set, right? So when you train over a larger data set, of course that bias is going to get smaller.
Gotcha. And for a given data set, the bias is expected or maybe guaranteed to be smaller than the variance of the naive?
No, that's not. No, there's no guarantee on that. Yes, in general, yes. There's no guarantee that the bias will fall within a certain precision from the real ground state energy. But what we can do is we can run things and see how it performs. And so far, it seems that it performs much better than the actual averaging of the measurements.
Okay, yeah, you mean that it's always sort of in a narrower span. I'm just wondering, because I want to know, if I use this technique, then how do I make sure that, I see a very, very small variance, but I'm not fooling myself because, well, maybe, I did something wrong and I'm, way off of sort of the accurate value.
But the great thing about this bias, it's that it's always positive. This is great because you are always guaranteed that your energy estimation that you get, well, if your the stochastic fluctuations are small enough, which can be improved by having a larger data set, you always guarantee that the bias that you get is always positive. So the energy estimation that you have, it's a upper bound on your ground state energy. Mm-hmm. Which is the spirit of variational algorithms, right? So it's the spirit of many techniques for classical computation of ground state properties. So we always try to get an upper bound on the ground state energy, right?
Right. Yeah. Thank you.
Okay. Thanks for the question. That was an interesting question. So,
and there was a question here where somebody says, I don't understand the bias issue. Maybe I'll just rephrase what you said. The bias just stems from the training of the neural network and is something inherent to it. I don't know if you have any more sort of intuition or insight to add to that.
Yes. So it comes from the fact, so what are we doing here, right? So what are we doing is we're minimizing this divergence to train this ansatz state here. Now we are drawing samples from the ground state, and so if we somehow miss the training of this ansatz state, what we can get is we can train so the outcome of that training can only be a state which has an energy which is higher than the actual ground state. So this is where the bias from the training come from. So it comes from minimizing this divergence here. And the reason why the bias is always positive is that however we can miss training of the actual ground state energy, we'll always train a state which is an energy higher of the ground state. Okay, so I hope that helps the answering the question. Okay, so let me move on. I think there is a lot of interesting things about this scheme that go also beyond the training, right? Beyond this training step. So actually, like one may think, okay, but hey, you are just training a classical model, so why don't you just run variational Monte Carlo on this classical ansatz that you're training? Well, it's not exactly the same, right? And the reason it's not the same is that because we are using samples from a quantum computer to feed a classical computation. So this fall into this quantum classical frontier scheme that I presented you at first for the averaging and then for the classical shadow idea. Okay, so here we have the same thing. So we are feeding to a classical computation measurement outcomes from a so data from a quantum computation. So if at every stage of this process we would need a classical representation of the quantum state that's going on in our device, of course this will be all classically we could simulate this classically at every step, right? But this is not what's happening. So what's really happening is that we still get a quantum advantage in this green part of the quantum circuit. So while we are executing these gates here that prepare, if you want, our quantum state at the end stages of a VQE or our ground state, if our VQE had got to the perfect solution. So we actually do not need a neural network representation of the state at this point. So in this gray part here, that's where we get the quantum advantage. Then on the last step, so do we need a perfect neural network representation of this step? Well, actually, not really, because we would need a perfect representation of this, the quantum state at this stage here with a neural network only if we wanted to recover all possible observables and all of them at infinite precision, which is not the task that we are really up to here. This, finally, this green part here is what we really want to have. So we only want to have a classical representation of a quantum state that allows us to estimate just one observable, which is in this case, it's the molecular energy or your many-body system energy up to a finite precision. And we want to do that with a polynomial-sized measurement data set. Okay, so it's really interesting, this handing of information from quantum to classical at different stages, and where do we really need a classical description of what's going on, right? Well, we only need a classical description from a polynomial-sized data set. And I think so this cartoon here, this scheme here, I think it even more clearly explained the combined quantum classical advantage that we have from this kind of scheme. So think of this yellow square here as the space of all quantum states. And this shadowed blue area here as the state, the space, which the part of the Hilbert space, which is efficiently can be efficiently described by neural networks. Okay, note that a neural network, of course, can always describe any quantum state if you allow to have an infinite number of weights and parameters, right? So what I'm labeling here, it's really the space of quantum states which have an efficient description in terms of a neural network. And then think...
what do you, sorry, quick
yes, question.
By efficient, I guess you're really specializing here to that particular psi parametrization you introduced a few slides ago.
Yes.
And efficient in the
yes.
sense of...
in the sense that, I can go back, yeah, in the sense that the number of parameters wij, hi, and ci and bj is finite, it's polynomial. Okay, that's what I mean by efficient.
Yeah, polynomial in the number of qubits.
Yes, parameters. No, sorry. Yeah, polynomial in the number of parameters. Yeah, if you parameters, and which also
parameters are
means
polynomial in the number of.
Yes, parameters
qubits.
are polynomial in the number of. The number of qubits, it's fixed by your problem. The number of parameters poly in the number of hidden variables. So yeah, I mean. I guess what I'm saying is that all the classical overhead that you have in this description has to be polynomial. Now the classical overhead here, it's composed by these weights W, Ci, Bj, but also these hidden variables Hi. So both the hidden variables and the weights have to be polynomial. Okay.
And that should always be less than something like, 2 to the n or so.
Yes.
Basically,
yes.
the number of parameters you would need to describe the yellow box.
Yes. Yep. Okay. Yeah. Thanks for the question. Yes, indeed. Also, of course, yes. Also, the number of hidden variables factors into the efficient description of quantum state by neural networks.
Mm-hmm. Good. Just a time check to let you know that we're at the hour mark.
Yes, I think yeah, we are good. Yeah, good time.
Mm-hmm.
So, okay, so let me now compare what we would do with a classical variational method so if you want a classical variational Monte Carlo, and what we are doing with this combined quantum classical scheme, right? So the scheme of VQE or your favorite quantum algorithm feeding a classical description of a quantum state. Now for a classical method, of course, we would start from an initial state, same for the quantum method. So an initial state which has a classical efficient description, And then, we run variational Monte Carlo, and maybe, the classical method gets stuck here, this red X here, because our energy landscape is particularly nasty. So we get stuck here and we can't move on. What we can instead do with VQE combined with this technique is that we could actually walk this part, this yellow part of this cartoon here, which is a part which is a part in which the neural network is not access to. Okay, when I say walking, so think of this path here as of the path that the quantum state undergoes in the final stages of a VQE. So this path here, it's really a path. If you want, it's like a diagram flow for this chart here. So while we are running this gray part, this gray circuit, quantum circuit here, we could be walking this yellow part, which is not, in which we do not need an efficient description of this state in terms of neural network. And then when we end, hopefully when we end here, so we could end in a region, which is this green region here, which is the region made up of neural network states, which have the mean value of h epsilon away from the actual ground state energy. Okay, so remember, what we need is just an estimation of the ground state energy, or an estimation of a good energy, that quantum state, which is epsilon away from what we see on with our estimator, right? And so that's the idea. So the idea is that this combined quantum computing classical machinery will allows us to walk a path in quantum states, which is not accessible really by classical computing. So that's where we hope to get our quantum advantage from. Right.
And Antonio, a quick question from the audience. This one might be a more general one. How does decoherence affect all this, or how do you cope with decoherence at this level, or is that just not in the picture yet?
Yes, no, this is not. The decoherence is not yet in the picture. Okay. Actually, let's say we're not considering yet. Okay, I'll just say that.
We'll come back to it.
Yes. Okay, so let me state these points again. So what we're not doing is we're not doing tomography with neural networks. Okay, so we're only interested in one observable, which is a critical observable for some algorithm that we want to run. For example, molecular energy, if we are targeting VQE for quantum chemistry systems. We're not correcting readout errors with neural network, which is something other people have done. And of course, as I showed you in the previous slide, what we are doing is not really equivalent to a variational Monte Carlo with a neural network classical ansatz. So what we are doing is, if you want a reconstruction of a quantum state with a neural network that only aims at reproducing sampling statistics, so if you want a mean value of target observable with finite precision. Okay, this is a far less demanding task than just doing like full tomography of that quantum state, which in general could be exponentially hard. Okay, then I would say there is a lot of open questions here. One of the open questions is, of course, yes, I think there's a question.
Yeah, we have a question from Will Livingston. I wonder if that's the Will Livingston I know from Berkeley. He says, how do you do the classical optimization on the path when the neural network can't actually accurately represent the state?
Yeah, I knew that that question was coming. So okay, so this dashed line. Okay, so let's be clear about it. Maybe there's a little bit of confusion here. So this dashed line here, okay, it's not the path of VQE. as it goes through different parameters. This is the path of the quantum state at the end of a VQE. Okay, so think about that. So we have already run our VQE. We have the optimal circuit for a VQE, and then this path is what the our state on quantum hardware goes through as you execute that optimal VQE circuit on the last step of the VQE. Okay, and then this yellow.
Yeah,
this yellow part, it's this. Sorry, just once. So the yellow part is the state of the of our quantum hardware as it undergoes these gray gates here. Yeah, I hope this. Okay. Yeah, it is.
So the black dot is representing the initial state. The
black dot is some initial. The black dot is some initial. Say if you want, is the Archery-Fock state, like some. Whatever state you want to initialize your classical or quantum algorithms with, you know.
Yeah, in the step. Yeah. Right.
Yeah. So I hope.
So typically your Hartree-Fock state, and then, okay, yeah, that makes sense then. And you run multiple cycles of this until you get to the final step.
Yes. So you would run. So maybe each time you would execute like a VQE, it will get you like to a different point of this region, hopefully every time crossing crossing the yellow region, and at the last step it would be this path here. Yeah, that's one I said. Yeah, I said it over here. It's in capital letters. So this is the path under one VQE circuit. It's not the VQE path.
Oh, I thought ONE was an acronym.
Oh, okay. That would be cool. I guess Zlatko, you can come up with a clever acronym for that.
One NISC air. I don't know. We'll throw that out there. Okay. So actually, yeah. So each time you run it, there's a separate little dashed path that goes from blue to blue, but may cross anywhere, you know, in the whole square.
Yes.
And you know, if you track the end of each dash path, that's always inside the blue region, and you're taking some gradient within that. But within each realization, as you're running the algorithm from the Hartree-Fock initial state to the final state where you measure the observable, you know, you can go anywhere in the larger Hilbert space.
Yeah, exactly. I hope that clarifies the question. Yeah, maybe I should have drawn like several paths and then something that connects them. But yeah, I mean, I hope the question is clarified now.
Right. And I guess the point is that the classical computer is stuck to the solid line and can never explore that larger space. So it may its gradient or its optimization is somehow more constrained.
Yep.
Okay, good.
Okay. All right. So of course, there's a lot of open questions here. For example, one open question is what is the size of this green area here, right? So how big is this green area, and you know, can we have any insights on what kind of problem we can even like hope to address with this combined quantum classical scheme? Well, yeah, we have run some classical computations to have kind of like a feeling for what that green area is. So what we have realized is hey, so this training thing that we are doing from measurement from a quantum computer can actually be turned the other way around. So it can be used for classical computation of classical, like, you know, like running a classical Monte Carlo for molecules, right? So this is something actually people were struggling with. So it seems that people till like only recently have come up with ways of having fermionic neural network state. So if you want ways of getting to the ground state of fermionic systems, or you know, finding electronic properties with some kind of like variational ansatz which had like neural network in them. And so we actually thought about this and we say, hey, you know, maybe we can use these encodings from quantum computing to actually build fermionic neural network states that can later be used for classical computation of ground state properties for molecular systems and beyond, and fermionic systems. Okay, so if you want, we're with this study, we're answering like two questions. So one is a question from the quantum computing perspective, which is how big is that green area that I showed you in the bean plot before? And another question is a classical question. So how can we run, fermionic neural network variational calculations? Well, we can do that again using the same quantum computing encoding that we use to formulate. These molecular Hamiltonians onto a bunch of qubits in the first place. Okay, so we did that. So we did this analysis, which is published in this Nature Communication paper, actually this year, and we found that we got pretty good results. This is the dissociation profile for two dimers, C2 and N2, in a minimal basis. If you're not a chemist, you can think of it as this is a 20 qubit problem. Okay, this is 20 spin problem. So we actually we got to an estimation of ground state of these problems, which actually goes beyond CCSDT methods on these minimal basis. Of course, this is not state-of-the-art computation for classical chemistry, but still, I think it's like to be the first implementation of this methods. I think it did a fairly good job. And this is the most complex problem that we solved, which I think it's water in the 631G basis. And again, if you're not a chemist, this is a 26 qubit problem. We still run variational classical VMC, and we got to a very good estimation for ground state energies, which went beyond CISD calculations. So yeah, this is the story is again is to get like a feeling on how well these neural networks, fermionic ansatz, perform for realistic systems. So with this, I think I'm done. I think we are still like borderline. Zlatko is kicking me probably out in a couple of minutes, but so I like to just thank both my external collaborators and the IBM team. External collaborators being Giuseppe, Giacomo, and Kenny from Flatiron Institute and University of Zurich, and the IBM team. Charles Hatfield, Sergey, Rudy Raymond, and Guglielmo Mazzola from IBM Yorktown Heights, Tokyo, and Zurich. Okay, so this is a summary of the ideas that I showed you in these slides. There is first two new classical quantum algorithms to target estimation of complex observables, such as molecular energies on quantum computers, which have the important properties of not increasing the circuit depth. First algorithm is based on the idea of classical shadows. We have worked that idea into a locally biased version of the original proposal, and we showed that locally biased version indeed performs much better. I mean, it performs better than state-of-the-art low depth estimators. Maybe I should have said estimators which really do not increase circuit depth. And then estimators can be built with this combined architecture of quantum computing and neural networks, which we get by feeding training of neural networks with measurement outcomes coming from quantum computers, and still performance of this mixed quantum classical estimator is fairly good, and improves up to 3 orders of magnitude in the precision compared to naive quantum computing estimators. And then at the end, as I said, we did some classical simulations which have an interest both from the quantum computing community, because we estimated again the size of that green area, which was the size of it gave us an idea on how well can neural network trained with samples from quantum computer approximate ground state energies of molecular systems up to a certain precision using a finite size data set, and also has some advantages from it's some interesting perspective from classical computing community, because we actually shown that this is a way of using neural networks for classical fermionic simulations, right? This is what we call the neural network fermionic quantum states. So I think, Zlatko, so with that, I'm done, and I'd like to thank you for, I guess, reporting the questions from the audience and making some questions of your own. I think they've improved the quality of this presentation. So thank you for that. And I also like to thank all the people that have tuned in for this, to follow this talk. So yes, I'm done. Thank you.
Thank you, Antonio, and I'd like to thank the audience for the many questions and very active discussion today in the chat. Unless there are any final questions, I think we're pretty much coming up at the need to end mark because of all the nice questions and discussions. So I'd like to thank you, Antonio, again. And I think for those of you who want to go back and learn more about Antonio's talk, it will stay live online. So you can come back and look at it again. Antonio and I will both be lecturing at the Qiskit Summer School, and starting next week or the week after. Basically, ours is the second week. So take a look there as well. And we will see you next week at Friday at noon. And maybe a final word, Antonio?
Oh, yes. Of course, I'm looking forward to, having you at some of you, I guess, at the Qiskit Summer School. And again, as Zlatko said, I'm really excited by the turnout, right? So there's really a lot of people there. So I guess me and Zlatko will look forward to giving you the best presentation, right? Pedagogical presentation of quantum at IBM.
Yeah, and if this talk maybe was a little bit, had a lot of terminology and you haven't seen before, I think yes. Antonio's lectures in that summer school are exactly going to introduce all the basics to this. I hope. Yeah,
exactly. Yeah, it's going to be much more basic and we're really going to go slow and go in details through all the concepts for VQE and stuff like that.
Yeah, and I guess, Antonio, you're pretty optimistic continuing in this direction with quantum ML and chemistry and so on. What are your thoughts about the directions in which the field is moving?
Yes, as I said, I pointed out in the first slides that there is a lot of thought about, again, quantum machine learning, but maybe we can we can swim against the current if you want, and we can think of what can machine learning do for quantum.
That is
and
a good
in general,
message.
In general, I think it's always interesting to trying to work at the intersection of classical and quantum methods. I think, which should really start to mingle more the two fields. I think great things will come out. And also, again, last direction is maybe a classical computational scientists could try to see if they can learn something or get something from quantum computing algorithms. So in this case, it has been the mappings for fermionic quantum systems, but it could be other stuff. So maybe we should open the dialogue between the communities also in that sense. I think it would be interesting.
And I think that is a good message to end on. So thank you, Antonio. Thank you, everyone, for tuning in. Stay in touch with us, and we'll see you next Friday.
Thank you.